Welcome to surface integrals of a real valued function. We will look at the definition in a particular case with a parameterized surface and an example of evaluating such a surface integral. I am Ronald Johns. We will be looking at something of this form: the integral over a surface S of a function g of x, y, z times ds. In this video, we'll consider an integral of this form where g of x, y, z is a real valued function of the three variables x, y, and z. So we're using rectangular coordinates here. And S is a two-dimensional surface in three-dimensional space, R3. In our example of the integral of g of x, y, z ds over the surface S, our surface S in MATLAB or Octave is going to be the following. Z is this function of x and y, x plus 2y plus a half x minus 1 quantity squared, and we'll let the region span from x going from minus 1 to 3 and y between minus 2 and 2. The surface looks like this. It has a little bit of a curve to it, as we can see here. Some MATLAB code that would generate this surface for you with this graphic is the following. We could let x equal linspace minus 1 comma 3 comma 10. That means that we'll have equally spaced values of x stored in an array. The smallest value will be minus 1, the largest value will be 3, and there will be 10 values in this array. Similarly, we'll let y go from minus 2 to 2. Then x, y equals mesh grid, the x and the y values here, those two arrays. And then z equals x plus 2 times y plus a half times x minus 1 squared. Use a dot caret for squaring this array x minus 1. X minus 1 is the same as the array x, except you're subtracting one element from every array element in x. Then we will produce this graph by using the mesh function, mesh x, y, z. Color map 0, 0, 0 says that each point in this mesh has red, green, and blue values of 0, which means that this graph is in black. No color, no red, no green, no blue. In our integral over the surface S, we're going to let the integrand be x minus 2y plus 3z. And so the question then is, how do we define, and later, how do we calculate this surface integral, the value of this surface integral? And the answer, starting from the basics, is to write this surface integral as a limit of Riemann sums. Let's remember that this surface S over here is given by z equals x plus 2y plus a half x minus 1 quantity squared. We will set up the surface integral by using a parametric representation of this surface S. So we're going to define S in terms of parameters, so we'll have a parametric surface. That means that we're going to define x, y, and z in terms of two new variables, which we'll call u and v in this case. U and v are called parameters. So over here we have a region graphed in, let's call it u comma v space. The horizontal axis represents u, the vertical axis represents values of v. So u is going to go from minus 1 to 3, and v is going to go from minus 2 to 2. So here's the parametric representation of this surface over here. We'll let x be u, we'll let y be v, and we'll let z be u plus 2 times v plus a half u minus 1 squared. Let's remember that this surface given as a Cartesian equation was this stuff. But if we let x be u, that means that every x that we have over here we can replace with u's over here. And since we're letting y be v, every y that we have here is going to be represented by v in this formula for z. So we're basically introducing two new variables u and v, but they just happen to be, in this particular case, x and y. The formulas for x and y in some other problems might be more complicated than this, but since we're given z entirely in terms of x and y here, z is a function of x and y, we can just let x and y be called u and v, or if you want to, and hopefully not confuse yourself, you could just still call them x and y. So once again, here's our surface. Z equals this stuff for x between minus 1 and 3, y between minus 2 and 2. We're going to set up a surface integral, represent this surface integral as a limit of Riemann sums, that is, and the Riemann sums are going to look like this. It's going to be a double sum. The sum I goes from 1 to n, the sum j goes from 1 to m, g of x sub ij, y sub ij, z sub ij, times something we'll call delta s sub ij. If we magnify this little portion right here, we have subdivided this region, this surface, into small subregions, haven't we? Here's that subregion. Somewhere in that subregion we pick a point and we'll call its coordinates x sub ij, y sub ij, z sub ij. So this point is in this surface somewhere in this little piece. This region that's colored is going to be called s sub ij, and the area of this colored region we will call delta s sub ij. So what we're doing up here in this double sum is we're multiplying the value of the function at this point times the area of this little subregion. And then to get the double integral, we'll take the limit of Riemann sums that look like this as m and n both go to infinity, and the dimensions of all these little subregions, each dimension, the length and the width in this case, go to 0. We will be dealing with position vectors that depend on two parameters. But before we get to that, it's good to recall the one-dimension vector calculus situation, where we'll have a vector-valued function r of a scalar variable, which we'll call u. So here's a curve, and as u changes, this vector going from the origin O up to the curve will move along this curve. So r of u, let's assume, is the vector coming up to here from the origin, and if we increase the u value by delta u, then r of u plus delta u is the vector coming up like this. Let's let delta r be this vector shown in red here. And basically this delta r is just r of u plus delta u minus r of u. So here's what we can say. The delta r that we have here divided by delta u, this is a scalar, so it's vector divided by scalar, so this is a vector value here, is approximately the derivative of r with respect to u, which we can write as r prime of u. Now take the equation with the first quantity here and the last quantity over here, multiply both sides by delta u, and we get that delta r is approximately r prime of u times delta u. So let's make sure that this makes sense. Delta r is a vector which is illustrated right here. R prime of u is also a vector, and we're multiplying that vector by a scalar. Often when people talk about linear algebra, they'll have scalar times vector, but we'll write it in this order. So now let's consider the Riemann sums that you would have for estimating the surface integral of g of xyz ds. Here's an illustration of the situation. This is part of the surface over here, and this is a little subregion. We'll call this subregion S sub ij. We'll let the area of this subregion be delta S sub ij. And let z sub ij equal z of x of ij, y of ij. Z is a function of x and y, and we're using this functional notation to constrain the value of z so that that particular x, y, and z value is on this surface, and in particular, it's in this little subregion. So the Riemann sum looks like this. The double sum over I and j of g of x sub ij, y sub ij, z sub ij times an area component, z sub ij. We'll take the limit as m and n up here, the upper limits, go to infinity, and the widths, or all the dimensions, maybe I should say, of these subregions go to 0. So that will define this surface integral in terms of a Riemann sum. But to evaluate this, we need to be able to calculate, or at least accurately approximate, the area of this little region. This is a region on a surface which might not be flat. But if these dimensions are small enough, then this region will appear kind of flat, and what we would have here is approximately a parallelogram. So finding the area of this region, if you wanted it exactly, is slightly tricky, but what we'll do is use an approximation instead. Think of this region as being sides of a parallelogram, and the parallelogram can be defined by two vectors, a and b, and the angle between them. And we can let h be the height, the perpendicular height from this edge up to this edge for that parallelogram. H can be found in terms of a, b, and theta, as we'll see in a minute. So let's remember that the area of a parallelogram is equal to the base times the height. Okay, the base in this case is going to be this side, and so that's the length of b, times the height, which is this length right here. But the height is a sine theta, the length of a times sine theta for this right triangle over here, just using the definition of the sine function. But then, if you have the norm of a times the norm of b times sine theta, we can remember that that is equal to the norm of the cross product of the vectors a and b. So the area of this parallelogram is approximately, the area that we have up here is going to be approximately the norm of a cross b. The area of this parallelogram that we have here, this kind of flat parallelogram, actually would equal this, but we're doing an approximation of this thing that looks like a parallelogram, but it might be just slightly off. And so I'll use approximately equals here just to be safe. So let's remember we're going to parameterize our surface so that we can evaluate the surface integral. So what we'll do is introduce a parametric representation of that surface S. We'll let x be a function of two variables u and v, y will be a function of u and v, and z will be a function of u and v for some region R, for some region in the UV plane, so that these points R and R. And so this we can write as a vector valued function. R of uv is the vector x of uv, y of uv, z of uv. And if we look at a small region R in the UV plane, then if it's small enough, it will map into a small region in that surface. Call it S sub ij. Let's let A and B be the two vectors that approximate the sides of a parallelogram by being tangent to this curve and tangent to this curve at this point right here, R of u sub I, v sub j. Then, by the approximation that we saw before, the length of this vector is approximately the partial derivative of r with respect to u at that point times delta u sub I. The length of this vector, actually this vector is approximately the derivative of r with respect to v at that point, and this thing right here is a vector multiplied by the scalar delta v sub j. So then we have A being one of the sides of the parallelogram, B being the vector, the other side of that parallelogram, and we will approximate the area of this little subregion by looking at the norm of the cross product of A and B. So let's go back to that surface integral which we approximated by this Riemann sum. Well, we now know in this Riemann sum the sum over I and j of g of this point times the area of the ijth subregion. The area of this subregion is just the norm of the cross product of these two vectors. And so the Riemann sum for the integral can be written this way. And then, just to make the notation perhaps a little bit simpler, let's write this partial derivative, partial of r with respect to u, as r sub u. And let's write the partial derivative of r with respect to v as r sub v. And so we have this Riemann sum approximating the integral of g of x, y, z ds. Well, if we look at this Riemann sum, delta u and delta v, delta u sub I, delta v sub j here, are the dimensions basically of, let's say, this little rectangle down here. And that's mapped over here where this area was what we saw over here. So in any case, we can think of this sum right here as being a double integral over this region R, because we're looking at all sorts of r sub ij's in here for the areas, and because that's the delta u sub I, delta v sub j right here, but we're multiplying it to get this area up here by the norm of this cross product. Okay, so to make a story short, the surface integral in that case is going to be the integral over the rectangle R of g of x of uv, y of uv, z of uv, times that cross product, times the differential of area, which is used in this UV plane. So here we have a formula for the evaluation of a surface integral. We have to find a region in the UV plane. We have to find coordinate transformations that will map that into XYZ space, into the surface that we want to integrate over. The surface down here, maybe we can call it R. The surface up here, we are calling that S, obviously. And so we get this formula, surface integral in terms of a double integral. So now let's consider a problem. Let's evaluate the surface integral of x minus 2y plus 3z ds, where S is the surface given by z equals f of xy, equals x plus 2y plus a half x minus 1 squared. And this surface will be given by this equation. Z is a function of x and y for x between minus 1 and 3 and y between minus 2 and 2. Here is a representation of that surface. So what we can do then is look at this equation here, and we can say, well, let's let u be x, let's let v be y, and then what will z be? Well, if I plug in u's for the x's here and v's for the y here, we get that z is u plus 2 times v plus 1/2 u minus 1 quantity squared. And so the mapping then is r of uv equals the x component of the vector, which is u, the second component of the position vector, which is just v, and the third component of that position vector, u plus 2v plus 1/2 the quantity u minus 1 squared. And since u equals x, and x is between minus 1 and 3, that tells us that u will be between minus 1 and 3. And since v is equal to y, and y is between minus 2 and 2, that tells us that v will have to be between minus 2 and 2. So if we differentiate this function, if we differentiate it first with respect to u and then later differentiate r with respect to v, let's see what happens. Well, let's look at the partial derivative of r with respect to u. We'll differentiate each one of these vector components with respect to u. The derivative of u with respect to u is 1. The derivative of v with respect to u is 0. The derivative of this stuff over here with respect to u is going to be 1 plus 0 plus 1/2 times 2 times u minus 1 to the first power. And that just turns out to be 1, 0, and u. If we differentiate r with respect to v, the first component differentiated with respect to v is 0, as we have up here. The second component differentiated with respect to v is 1, which we have right here. And when you differentiate this third vector component with respect to v, you're just going to get 2. And so the partial derivative of r with respect to v is the vector 0, 1, 2. Now, we know how to take, hopefully, cross products of vectors, and we will short circuit the procedure by using computer software. We'll use SageMath. So here's what we'll do to calculate this cross product, which I claim turns out to be minus u, minus 2, and 1. We'll first define u and v to be variables, and then r of uv is a vector which has the components that we had right down here for r of uv. And then ru is going to be the derivative of r with respect to u. And then we'll print out what the value of ru is, and it tells us that it's going to be 1, 0, and u, which is what we have up here. We'll do something similar with differentiating with respect to v. Rv will be the derivative, the partial derivative of r with respect to v, and then semicolon is the end of that command. And then we'll print out the value of Rv, and it turns out to be 0, 1, and 2. It's written this way because we actually had these being functions of u and v up here, I guess. Okay, now how do we find the cross product of r sub u and r sub v? In SageMath, we'll do it the following way. We'll say r sub u dot cross product of r sub v. So this notation will find the cross product of ru and rv, these partial derivatives up here. I'll store that cross product in another variable which I'll call RC. And then in the next command in SageMath, we'll just see what RC is. And it turns out to be minus U, minus 2, and, and 1, which is what we have up here. To calculate the surface integral, we need to find the norm of the cross product of these two vectors. And the cross product of these two vectors we saw before was this vector. And the norm of a vector is the square root, which we have here, of the first component squared plus the second component squared plus the third component squared. So that's going to be u squared plus 4 plus 1, which simplifies to the square root of u squared plus 5. So now, to get the surface, to evaluate the surface integral of this function, x minus 2y plus 3z ds, over that surface S, we will evaluate it by looking at the double integral over the region R of what? Well, we need to get this function of x, y, z in terms of u and v. And so let's see, x is equal to u, so that's here. Minus 2y is equal to minus 2v, which is right here. And 3z is 3 times, and then z was equal to this stuff in terms of u and v. And then we have the norm of that cross product, which is right here, dA. And so now we'll change this to an iterated integral. The integral where u goes from minus 1 to 3, of the integral where v goes from minus 2 to 2, all this stuff that we saw up here before, and then we'll integrate with respect to v on that inside integral, and we'll integrate with respect to u on that outside integral. And the value of this integral, which would probably take you an hour to do by hand, is approximately 292. So let's see what happens if we look at the SageMath calculation of this. First of all, just to check what we have up here, the norm of the cross product. The cross product was stored in RC, so we can evaluate that by RC.norm with parentheses. And it tells us that it's the square root of the absolute value of u squared plus 5, which is basically what we have here. Now you might wonder why there's an absolute value in here. My guess is that SageMath is being safe just in case we happen to have complex numbers here. But in any case, we are using real numbers, so the absolute value of a real number squared is just that real number squared. So this checks out. And then we're going to define a variable z, and I'm going to let z of uv equal u plus 2 times v plus 1/2 u minus 1 squared. That's what we had up here. This z, remember, because we're looking at this surface S, this z right here was u plus 2v plus 1/2 u minus 1 squared. So we're just substituting that in for z when we come down to here. So we're now going to integrate the, let's say we're going to find the integral of the integral of, and then we'll have the u minus 2 times v plus 3 times z, where z is this stuff in terms of u and v, remember? And we're going to multiply that by the norm of the cross product, which was this stuff right here. And this inner integral is going to be integrated with respect to u, going from minus 1 to 3. This outer integral over here is going to be integrated with respect to v, going from minus 2 to 2. When we integrate that, here is the value of that double integral, which is also, remember, the value of this inner integral. Now, this looks kind of complicated. We have, for instance, some square roots of some numbers here, a hyperbolic arc sine of something fairly complicated here, and another hyperbolic function here, the hyperbolic arc sine of this also. I'd like to know what this is as a number, and here's how I can do it. I can use an underscore, which represents the previous answer, which was all this stuff up here, and then point n with parentheses. This point n with parentheses gives me a decimal approximation of whatever the value of this thing was right here, which is this thing right here. And it turns out to be 291.998 something. Okay, as you can see, this is very close to 292, which explains why up here we said that this integral is equal to 292 approximately. Okay, one more thing that we should notice is a slight difference between SageMath and up here. In this integral, I had v being integrated first and then u being integrated second. But I did it in the reverse order down here. I integrated with respect to u on the inside, and then I integrated with respect to v on the outside. Basically just switching these two integrals and switching this, instead of dv du, we have du dv. And in this particular case, this would not make any difference in our calculation. So what did we do in this video? We introduced the parametric representation of a surface. We used the parameters u and v in our particular example. We wrote our surface integral in terms of Riemann sums. We recognized those Riemann sums as an approximation of a double integral. We wrote down that double integral and evaluated it as an iterated integral. And to put everything together, the formula that we had for going from the surface integral to a double integral, the surface integral is of a function g of x, y, and z. This double integral is just a function of u and v, and so the surface integral of g times ds was the integral over r of this function of u and v times the cross product of partial derivatives of our position function, position vector, dA. And then once we had this double integral, we were able to write it as an iterated integral, and at least in theory we could have evaluated that iterated integral by hand, but in our case we decided to use SageMath software to do that calculation for us. I hope you enjoyed this presentation, and I hope you look forward to seeing the next one. Have a good day.